everyone, and welcome back. Today, we're going to talk about proper problem-solving technique for physics problems. While we're here, there's something else that I would like to discuss as well. Throughout this program, I'm going to give you lists of either rules or guidelines that will help you become a better physics student. We are going to talk about two of those lists, so please get your notebook out and ready to go. The first list is going to be very general and can be applied to any physics problem you do, literally ever. The second list is going to be much more specific. Now, let's talk about our first list. Basic questions to be asked for any physics problem. These are questions you should ask yourself before putting pen to paper for any physics problem you deal with. The first question, what object or objects are you tracking? We've already talked about some variables like velocity, displacement, position. Now, if you are talking about velocity, displacement, or position, you need to know what object you are talking about. In physics, you're typically tracking a single object at a time, especially if you're first-time physics students. You're tracking one object. You need to identify what that object is. There are some subjects later on where you are tracking more than one object, but typically in a physics problem, you are tracking one object at a time. If the situation is a baseball game and you have the velocity of the bat and you have the displacement of the ball, that is typically not going to be any good to you. Because if you are predicting an outcome, you're either predicting an outcome about the bat or you're predicting an outcome about the ball, which means you need information on one and not the other. Second question, when does the problem start? And third question, when is the problem over? I would say about 90% of the time, these questions are very simple to answer, and they take no more than a few seconds to go through in your head and find the answer to each of them. But for that final 10%, these questions become extremely important and sometimes are not easy to answer, particularly the second and third questions. While we continue, I'm going to take those and put them in the lower left-hand corner here so we can reference them as we move forward. Now, this next set of rules is designed for any physics problem that deals with any kind of mathematical values. As you're going to hear me say multiple times, physics is not a math course, but there is math in the course. You actually need to know the math before you enter this class. Physics is teaching you how to use it as a tool. That being said, there are things you should be doing to make sure you have good habits in a physics course. So here is rule one. List your givens. What listing givens means is when you read a situation, you need to be able to pull out what information from the situation is actually important to you based on what you're trying to find. Some information in the problem may be worthless to you, and you need to be able to identify that. Each of my rules here is also going to have an addendum, a second part to the rule. The second part to this rule is you may need to convert the units as you pull out that important information. If you have a car going 3 miles per hour and someone asks you, how far has it gone in 2 hours? Well, the math is pretty simple. But if someone asks you how far has it gone in 15 minutes, you would need to convert either the miles per hour or the 15 minutes so the time units matched. That is basically the idea here. Typically, you will be converting to SI units. But the truth is, for the math to work, the big rule is the units have to match each other. In the math, units typically cancel, and you can't cancel minutes and hours, for example. The second rule is write down your equation. When you take an exam, like the AP exam or something in college, you will typically be given an equation sheet or allowed to make your own. Like I said, this is not a math course. You are not expected to memorize mathematical equations in a physics course. They will be given to you. The question is, do you know what they are and how to use them? And one of the first ways you can actually show your grader that you recognize what topic you're on is to write down whatever equation or relationship that deals with that particular topic. So write the equation on the page. Second, you need to solve for whatever variable you are looking for. The one mathematical skill you need here is algebra. And the biggest rule for this is if you're going to use a mathematical relationship, you can use it as long as one variable in that relationship is missing. And that variable can be anywhere in the relationship. Rearrange for the variable you are looking for. The third is plug and play. Once you successfully do numbers 1 and 2, you will take the givens that you have found, you will take the solved equation that you have created, and then you will combine the two and search for whatever variable you are looking for. My addendum to rule number 3 is to keep your units in your work. Physics is not a math course. Now, of all my rules, this is the one that I have difficulty trying to get across for people to understand. So let me try to explain this. There are a few reasons for this. Number 1, if you were to look back on your previous work and all you saw was a page of numbers, it would be very difficult to take a look at your work and see what was what. However, if you do all your work with your units, you can look back at your work and see very easily, this is a mass, this is a velocity, this is a time, this is a displacement, because everything would have units. For the exact same reason, someone who is assessing your work needs to see this. They need to see that you understand what these variables are and how they relate to the real world situation that you are given. The other reason for doing this is much more subtle, but probably much more important. Every time you write down a number, your mind says, this is a number, 5, 20, 34. However, every time you write down a number with the unit, your mind says, this is a mass, this is a velocity, this is a time, it is 5 kilograms, it is 24 meters a second, it is 53 minutes. And this builds up something in your subconscious that is actually quite important. It builds up a type of muscle memory. Someone who plays a sport, like baseball again, if they want to be good at bat, they don't just do a couple practice swings and then go play in a professional game. They practice their swing constantly. They have practiced their swing thousands of times for every one time they swing it in an actual game. And they do this so when they're actually in the game, their body actually moves unconsciously. This is what you need to do to your mind if you want to be really good at physics. Your mind has to be able to recognize what these variables are and how they relate to the real world situation. And the easiest way to gain that muscle memory is to keep units in all of your work. So we're going to take these 3 rules and put them in the lower right-hand corner. And now I'm going to show you how to actually work with them. And to do that, we need an actual problem, and we're going to use this one. A 13.5 meter long bus is moving with a velocity of 79.2 kilometers per hour to the east. It's on a road that is 300 meters long. The driver steps on the brakes for 3.8 seconds in order to decrease the bus's speed. After the bus moves a distance of 74.1 meters, how fast is the bus moving? So let's do our general list very quickly. First, what objects are we tracking here? Well, we are tracking the bus because they want to know how fast is the bus moving after a certain distance or time. 2, exactly when does the problem start? The problem starts when the driver steps on the brakes. That's the start of this problem. It is not 10 minutes before that. When is the problem over? Well, the problem is over after the bus moves a distance 74.1 meters. We do not care about anything after that point. The bus could speed up, slow down, crash into a tree. After this point, we do not care. So we've identified what we're tracking, when the problem starts, and when the problem is over. Again, that is a general list that is good for any physics problem ever. Now let's talk about our more specific list that is designed for any mathematical physics problem. First, let us pick out and write down some givens. Now, these are things that are actually important to us. A 13.5 meter long bus. Now, the length of the bus is not important. We're looking for things like its velocity, how far it's gone, but this is not important information here. So I'm going to skip that for now. Is moving with a velocity of 79.2 kilometers an hour to the east. Now, this is good information. This is obviously my initial velocity. VI is 79.2 kilometers per hour. Now, east, I'm going to make a positive value. So east will be positive and west will be negative. It's on a road that is 300 meters long. Well, we've already said we're tracking the bus, so we're not interested in the road or how long it is either. The driver steps on the brakes for 3.8 seconds. Now, this is good information too, because it is our time. It is how long the bus is slowing down, 3.8 seconds, in order to decrease the bus's speed. After the bus moves a distance of 74.1 meters, that is obviously my displacement because they literally tell me how far the bus has gone, 74.1 meters. How fast is the bus moving? So we are looking for velocity final. And we already have a key as to what our range is, and this is another useful skill in a physics problem. Before you even start doing anything else at this point, you should have a general idea of where your answer is going to end up. And for this problem, the hint is the fact that the driver steps on the brakes and the bus is slowing down. It's decreasing speed, which means we should expect an answer that is less than 79.2 kilometers an hour and still be positive, because stepping on your brakes doesn't make your car go in the opposite direction. So in the very least, we have a general range that we expect our answer to be in. If we end up with an answer that's, say, positive 84 kilometers an hour, then that's a big red flag. So looking at my problem, it's generally a good idea to read it more than once to make sure you have the proper information. Anything else in this problem looks like it is not useful information. So I'm going to move our givens list up here. All right, so step one, list givens. Addendum to the first step, convert units. So I have initial velocity, time, displacement, and my initial velocity units do not match neither my time nor my displacement. Now, all the units need to match. I could change seconds to hours and meters to kilometers, but I'm going to change the initial velocity, considering you're typically going to want to go to SI anyway. So let's convert the initial velocity so all our base units match. To do that, I'm going to use what I call the chain method to convert. I know this goes by a couple other names. Each chain, I'm going to convert one of my base units. So first, I'm going to get rid of kilometers. And since kilometers is on top, I'm going to put it on the bottom, my first link here. I'm going to go from kilometers to meters. There are 1,000 meters and 1 kilometer. The top has to match the bottom. And this is going to get rid of my kilometers and leave meters as my unit on top, which is what I want. My next link, I have hours on the bottom. I'm going to put hours on top. I want to go to seconds. 1 hour is equivalent to 3,600 seconds. I have hours on the bottom. On top, they cancel, which means I have seconds on the bottom, which is what I want because my goal is to get meters per second. What I've created is basically a conveyor belt. I will take the 79.2 kilometers an hour, multiply by 1,000, divided by 3,600, and I will end up with 22.0 meters per second to the right or to the east, which I've defined as positive. So number one is done. All my givens are listed and all the base units match. Meters, meters, seconds, seconds. Number two, write our equation. Well, so far we only have one equation that we've derived. Displacement is 1/2 VI plus VF times time. This is my average velocity equation, where 1/2 VI plus VF is literally average velocity. In this equation, let's check off what we have. We have displacement, we have initial velocity, we have time, we are missing VF, and this is what the problem is actually looking for. Because remember, we were asked, what is the final velocity of the truck after the braking period? I'm going to take this and rearrange for the variable I am looking for. So we're going to do a little algebra here. First thing I'm going to do, and actually this is a good general rule, get rid of any denominators. I have a half right here, so I'm going to get rid of that too. I'm going to multiply 2 on both sides. That would get me 2 delta D VI plus VF times time. I'm after VF, and a good general rule is to get rid of anything near it. Next thing I want to get rid of is this delta T on the side. So I'll divide by delta t on both sides, which will give me 2 delta d over delta t equals vi plus vf. And to get vf alone, I would have to subtract vi, which would give me 2 delta d over delta t minus vi equals vf. Although I'm going to put the equals vf on this side because we're about to work with this. So this is my rearranged equation for the variable I am looking for. So why do this? Well, there's a few reasons. One, being able to rearrange the equation like that is a very, very useful skill and one that needs to be built and practiced. On standardized tests, it is very typical that you are not even given numbers. This is what you're expected to do. Depending on what variables you are given, can you define what you were looking for and show us how to find it? Now, in this particular case, you were given numbers, which means there's another reason to do this. If I actually now rewrite this with the values and the units, which was one of my rules, 0.1 meters over 3.8 seconds minus VI, which was 22.0 meters per second, I can actually check my units as I work. I am expecting an answer in meters per second here. Just by looking at this, I have two numbers here which will be subtracted. The first one, literally, 2 has no unit. This is meters divided by seconds. So I do this, and I will get 39 meters per second minus 22 meters per second. This is evidence that I'm on the right track, and I end up with 17 meters per second. This is the final velocity of the bus after that time period. Keep in mind, this was a pretty simple example because it was your first one. And right now, the most complicated unit you have is meters per second, which isn't complicated at all. Later on, you're going to have units that look like this. So being able to do unit tracking, which means follow through your units and recognizing what everything is as you work with it, is going to be a very useful skill. All right, so quick recap. The first 3 rules I have in the lower left here, these are good for any physics problem ever. What object are you tracking? When does the problem start? When is the problem over? Those 3 questions should be asked all the time. Most of the time, they are very simple to answer, but every now and then, they are not simple to answer at all, and they become much, much more important. For any physics problem where you're dealing with the mathematical equations, you should be using these 3 rules. 1, list your givens, the addendum to this one, convert units so all your units match. 2, write down what relationship you're using, what equation you're taking from the equation sheet. The addendum to this one, solve for whatever variable you are looking for from the equation. Now, if you're really good at the algebra and can do it in your head, you can skip the first part of this and just write down the equation with the missing variable. That is fine. 3, plug and play. Take the givens that you have found and converted, put them in the equation you have written down with units, solve through it, and find the final results. These techniques won't just help you get better at physics, but it is what is expected of you on a standardized assessment and in a college physics course. For example, on, say, the AP exam, if this was an open-ended question, it would be worth about 15 points. If you were to do all this in your calculator and put down the answer, which is positive 17 meters per second, or 17 meters per second to the east, you would get 2 points out of 15. Now, a lot of people would say, but I got the answer right. And you're correct. You got the answer right. But the answer is not what you were being assessed on. What you're being assessed on is whether or not you can do the process properly, because that is what a scientist needs to be able to do. They need to be able to work with the process and be able to communicate what they have found to other people. Simply putting down the 17 meters a second is not good enough. All of the work provided, not only that I recognized what was useful from the problem, but I knew exactly what relationship to use for what I was looking for, how to redefine that relationship. what the units were in my problem, and how to actually find the final result. I showed that I understood the process. And this is what a college program is looking for when they're looking for students. In the case of a professor trying to help you, if someone put down, say, 14 meters a second and nothing else, they got the answer wrong. But I, as a teacher, do not know how to help them then. If a student puts down the entire process and gets the answer wrong, then I could show them exactly where in the process that they had difficulty, and that will help them get better because they know exactly what they need to concentrate on. So these rules and guidelines are really designed to help you become a better physics student. And they're also designed to help whoever the instructor is to do their job, which is literally to help you become a better physics student as well. So I hope this lesson has helped you out. Have a good day. This is Mr. M signing off.